uh, thank you for coming back. Okay, yeah, I wasn't expecting that. Okay. Yeah. So, but all right. Okay. So what we're studying again is the maps from X to Y. Okay, and X and Y, you should think about as being, say, compact smooth manifolds. Okay, maybe with boundary. Okay, just so we're looking at good basic objects, right? I mean, nothing, nothing looks nothing very exotic. Okay, and we were interested in the continuous functions, and in thinking about it, then we realized that continuous functions, we can't ask ChatGPT about them, right? I mean, if I just have a continuous function, how would I even put it into the computer if I don't know anything at all about the function? I don't even know, right? I mean, you just give me the values at many points, and I could, and I don't know whether when I interpolate it, whether I'm anywhere near the function values, right? You need to be having a little bit more data before you could hope to understand what a function is. So what we did was, included in this, we looked at the Lipschitz functions from X to Y. And these are dense, and the inclusion is a homotopy equivalence. Okay, and that's that's sort of a very, very formal matter. To do. You could imagine that Y is, but we did it for the special case where Y was the sphere, and what was the main point, right? It was that there was a neighborhood of the sphere, right, where such that nearby points stay in the when you draw the arc connecting nearby, the chord connecting nearby points, it stays in that neighborhood. And that neighborhood you could deform back into the space. So for manifolds with boundary, you could also always do that. So close enough functions are always canonically homotopic. Okay, so this is somehow a reasonable thing from the point of view of algebraic topology, and we discussed the entropy last time. We talked about how much information is there in an L Lipschitz map. And in fact, we saw that the amount that there was exponential in L to the dimension of X. Right, that was, roughly speaking, the base of the exponential has to do with a little bit the geometry of Y, has to do with how close you want to be approximating functions, to each other, right? But if, all that's hidden in the X, but that, this is really what the volume of the function space is, the amount of information involved, okay? Okay, so what I want to now talk about is, for a given level, we think about these as being objects of a certain amount of complexity, right? And obviously, as L gets larger, right? This is getting more and more complex in some sense, right? If you'd be trying to store the object and understand it from any coherent point of view, right? It's obviously growing. So the question is, what really happens? Okay, so I want to do some case studies. Oh, okay. Okay. Yeah. Okay. So let's first consider. Okay, this one is a little bit pathetic. And if I were going to map from X, so that one already violates. You see, I'm not so consistent here. Right? Okay, so I'll be consistent just for the sake of being consistent. Okay. Okay. Right. So if I were going to map from X into an interval, right? This is kind of pretty boring, right? And of course, if F and G are L Lipschitz, then so is Tf plus 1 minus Tg. Okay, right? So what's just happening is, from the point, this filtration, right? So we're going to be filtering this by the Lipschitz constant. This filtration is insanely boring, right? I mean, right, at every particular level, it's contractible, okay? And, I shouldn't say it's boring, but, sort of the geometry of this, right? There's a nice convex geometry, and of course I made a choice of a Banach structure. So there's something that could make your geometric soul sing, but that's not what we're focusing on, okay? And I could play around with this if instead of doing this the interval, suppose that I did, I could put another metric on the interval, where it's sort of, I'm imagining the metric it induces from the plane rather than, or the Riemannian metric, okay? So then all of a sudden there begins getting to be some geometry, because if x is 2 points, if I map these 2 points, I will have to increase the Lipschitz constant some in order, in order to, right? When I want to null homotop the map, right? I say, compare it to the constant map that goes there, right? Then obviously I have to, go through that bulge somewhere. Okay, right? So, okay, so so for this version, each sublevel set is convex, but when I change the metric, it's more that the L Lipschitz maps included in the L plus the bulge become null homotopic. Okay, right? Right, it's not that, if I want to be still doing topology, right? Which you could say, well, make up your mind. Are you doing geometry or are you doing topology? But I can't make up my mind, so I'll constantly try to go back and forth. So if I want to be looking at notions that are going to be, somewhat insensitive to the metric on the target, right? The moral of this very, very simple example is that I can't just fix one scale. I'm going to have to look at the interaction among the scales. Okay? So, okay. All right, so this seems to be as good a moment as I can, and now I'm going to introduce what's called persistent homology. Okay, and this is just a little bit of formalism, and I'm not going. It doesn't really. So let me just draw. Okay. Okay. So here's a space X, which happens to be the real line. Okay. So this is going to be of X together with a function. Okay. So. Okay, and I'm going to draw the traditional picture that people draw in Morse theory. Okay, and then I'm just going to, wave my hands and say that we'll just call something a different name, and then it's just a change of point of view rather than any new mathematics. Okay, the only new mathematics is a tiny piece of linear algebra. Okay, so what's happening? So I'm going to look at. For the moment, just pH0 of xf, because the zero-dimensional homology everybody knows about, that's basically the components of the space. Okay, so now so we're going to ask what happens at various levels, right? So below this level, we always have the empty set, so the persistent homology is 0. Okay, once we get to this level, right, what's happening is, right, the sublevel sets are always just connected, right? So I have, I don't know, I guess I should pick a field coefficient. Okay, so it's just whatever the field is till here. Then at this moment, right, at this level, there's a magic level where all of a sudden I get 2 copies of K. All right? Okay? Right? And now, where was anything persisting or not? Well, I mean, of course, the sublevel set at this size is included in the sublevel set on that side, right? So there are maps, going upwards. If we're doing homology, they'd go downwards if we were doing cohomology, okay? All right, and there are people who make a fuss about that point, but I'm certainly not one of those people, okay? And now, you just keep on going until you hit the next critical point, okay? And what happens there? Well, once I go above this level, right, I'm again connected. So above this level, I just have the vector space itself. Okay, and now here I'm going to use linear algebra. Okay, I can break this up into pieces. In one piece, the map from K to K, right? What goes all the way from the bottom lives all the way to this level, and forever after in this picture, it's just K. Nothing ever changes again. Okay, so there's something that goes from the bottom all the way up to infinity. Okay, and then there was a moment where you had a 2-dimensional vector space, and it moves into a 1-dimensional vector space. So something dies. Okay, what dies? Well, it's the 0 cycle that's this critical point, P2 minus P1 or something, right? I mean, this difference of critical points, okay, so this is sort of the funny little piece of linear algebra, right, which is that, that only societies are existing at any time. It's just that when someone dies, then you identify, the basis that you choose, right? Who is it that, what is the new guy, right? So there's something that lives at this time and goes on forever. And in addition, there's some guy here that was born at this moment and died there. Of course, you don't know who it is that dies until the death takes place, right? I mean, okay. So this is called a barcode, okay, because these are bars, okay. So you could formalize it. It's a functor from the real line, viewed as a category, where there's an arrow connecting things that are appropriately ordered, right? I mean, and it's something like that into vector spaces. And then there's a simple statement that everything is a sum, it's like modules over a PID. Everything is a sum of very, very simple modules. And you can encode all of those into barcodes. Okay, and the bars are, I'm going to ignore little nuisances about whether they're open intervals or closed intervals. That has to do with whether you're setting your sublevel sets to be less than or equal to or equal. Okay, all of those are way too refined to worry about. I mean, or maybe you worry about them, but then you never want to talk about it. Okay, so, you make some decisions, and there are sort of finite length intervals and infinite length intervals. Okay, right? At the smallest level of crudeness, right? And that's one thing you can notice. Finite length versus infinite length. Okay, so does everyone get the idea? I mean, I think the picture is clear, and then it's clear that you also have to do a drop of very simple algebra to make this make sense. Okay, and that then you do get something that's well defined, right? I mean, this breakup is well defined up to isomorphism. Okay, so this is, so if I have a space with a filtration, this is the kind of object I get. And the key point that enables me to get this object is just the most trivial thing, that F inverse of one level versus F inverse of a higher level, that one is included in the other. I mean, whichever way it works, okay? Okay? So, for example, if the function F is less than or equal to the function G, then there's a way of comparing the persistent homology of X with respect to F and the one with respect to G. Okay, so if I'm looking at less than or equal to L, wherever G is less than or equal to L, F is less than or equal to L, so then I get a map in this direction. Okay, and if F is, if the difference between F and G is bounded, okay, then I get a map from this the other way up to a shift. Okay, so let me just comment. So the persistent homology of F is a barcode, okay, and the bars have lengths, okay, and if F minus G is less than some constant, okay, the bars more or less coincide. Okay, you can gain or lose bars by shrinking or expanding by C. So if I take this example, and just over here, I'm going to make a new function. I put in a little bump. Okay? I mean, this is the whole math. Okay? I mean, it's, there's nothing much to say here. If I put here a bump of size B, I guess I should call it a bump of size C. What I do is I create one new interval. Okay? And that interval has size C. Okay? Okay? Or if I just take this whole function and I shift it up by C, all the intervals move by C. Okay, so that's all that can happen. You might create some things, you might throw things away. If you're dealing with intervals of length bigger than C, then you're not going to be able to throw it away. You might be able to shorten it, but not down to nothing. Okay? So if you like, you could say, not only is this a functor in some category, it's also a function which is continuous in some sense, right? That if the functions don't differ by much, there's a sense in which these barcodes don't differ by much. Okay, and there's a thing. It's called the bottleneck distance that have to do with trying to move one to the other. But I think everyone understands it. And it's much easier to not actually give definitions or prove theorems or anything like that. There are lovely sources, there are countless sources in the applied literature. Maybe I'll just mention, where this idea first occurred, to my knowledge, in the pure literature. It occurred in three places independently in the applied literature. Some people were doing things about proteins. Another person who was doing things about trying to do automated computer maps of snowfields in the Arctic. And in all the cases, so let me just say, one key thing about this is, so the bars of infinite length, okay, so let me just go back to math rather than history, right? The bars of infinite length, those are the topological invariants, right? And that's what you usually study in Morse theory, right? You want to say, I'm going to use a function in order to study the topology of a manifold. Okay, right? And you look at some really good function and you discover things about the manifold, and that's really looking at the things of infinite length, right? Those are the things that survive. If X is compact, so then you go right. Once you go above there, there's nothing much more to talk about. Whatever survived to there is really the homology of the space, and all of those bars then go to infinity. So the infinite length bars was topology. And the rest, you say, oh, that's some kind of noise, that maybe your function wasn't maximally efficient from the point of view of understanding topology. Okay? But now you realize that, when life gives you lemons, you make lemonade. And you say, oh, instead I'm going to now have a more refined invariant than just homology, and I'm going to call it persistent homology. It's going to have all of these extra bars, which are going to be, some of them are going to be small, some of them are going to be large. And they're useful for studying functions when they're functions on spaces that you already know about, or something like that, okay? So the Morse inequalities, are typical, so there are Morse inequalities about these things. So this is sort of nice because here, whenever you go through a critical point, it actually is reflected in the persistent homology, unlike in Morse theory where sometimes, you don't know, right? I mean, it might be giving you something that's spurious and ultimately dies, or whatever. So this is sort of a good and interesting thing. Okay? So so this is the kind of thing that would be useful for us to study, and I'm kind of interested in the persistent homology of these function spaces. Okay? And so let me just make one formal remark. So instead of looking at the Lipschitz functional, right? So here I was taking the Lipschitz constant going from here to the real numbers. Okay? What I'm instead going to do is take log of the Lipschitz function. Okay? This is just cosmetic because, it's clear you could translate information back and forth. The big advantage is if I have two different metrics, right, say on 0, 1, and I consider it either 0, 1 or 0, 2, right? So then the metrics are related to each other multiplicatively, right? Two metrics inducing the same topology, right? I mean, if I was going here, I was saying I'm taking smooth manifold, so the two metrics infinitesimally, the relation between them is some, there's some constant about, how the sizes of balls, and then I'm maxing that over the manifold. So these two things differ multiplicatively, so when I take log of the Lipschitz constant, I get something that's well defined up to an additive constant. Okay? And which means that if I would be able to ever compute the persistent homology of the function space, then it'll be well defined up to some finite amount of stuff. Okay? Yeah. Yeah.
In applied literature, these bar diagrams, they correspond to, they grow out of the refinement of subdivision of the manifold.
Yeah. Yeah, so
In your presentation, it's somehow connected to Morse one.
Right, yes.
I fail to see the connection.
Okay, yeah. So say a typical application might be, I say have some space or other, and then I sample it with points, okay, or there's some data about something where each point is a point in R100 because I did 100 measurements of something, and I'm interested in the relations among them. Okay, so I don't actually get to see, right? I mean, I only see samples. I don't actually see the whole space at once. So one of the things that people do in this topological data analysis is they try to infer what's the shape of the aggregate from which this data came from. So one way to do it is, you think about these things, and now I'm supposed to give you a function. So I have now this point cloud in, say, R100. So I'm going to think about this as a function from R. So from the points, I'm going to get a function from R100 to the real line. Okay, just by taking the distance to the point set. Okay, so what happens? So at level 0, I'm just getting the point cloud. Okay, and so that's just dust. At level infinity, I'm just getting, Euclidean space, so everything's dead then. Okay, but now, suppose it came from some decent object, and this thing was reasonably well sampled from it. Okay, there's going to be sort of the Goldilocks zone, right? Not too big, not too small, where you see where the sublevel set, right, will actually be an annular region around this. Okay, now there might be some imperfections because of outliers and things like that. So one has to worry about things, but that's sort of the idea. So then what you want to do is you want to look at the persistent intervals that are not too short, because then you're just measuring dust and maybe noise and stuff like that, and then and not too large because that's where all the signal got lost, right? But there's some zone in between. So so what they usually do is pick some threshold and look at the things that go from that threshold to twice the threshold or something like that. There's a certain amount of voodoo and I mean there are theorems, but the hypotheses never apply. So instead there are heuristics, and then if it works, you say that it was an application. If it doesn't work, you don't write any papers about it. Right? But, okay, I think I went beyond the scope of the question.
The example of this.
But anyway, the example is, so what you were describing about, taking points and then filling in, right? That really does fit into this thing about taking sub-level sets, right? I mean, just the sub-level, the function that I take is the distance to that point set. Okay? All right. Now, there's another way you could have done this, which is to go a drop more abstractly, which says you don't really need the function, you just need the filtration. And then what you can just do is ignore the Euclidean space and just say that at particular times, I'm going to put in, sort of more abstract simplices. So it starts off being dust. The first time that I have points of distance epsilon, then I'll put in an interval. If I have 3 points that are of epsilon, distance from each other, I then might put in a triangle. Okay?
So your level function is the size of this epsilon?
Yeah, and then right. So then you build an abstract simplicial complex from it, and then the simplicial complex's structure and the function on the simplicial complex are both coming simultaneously. So you don't really even have to mention the function anymore, but it is there. Okay, so yeah, and now that example, so here's a question that Furstenberg studied many years ago that led to Poisson boundaries, a lot of fantastic mathematics. He was interested if you had a lattice in a Lie group, does the lattice know which Lie group it came from? Okay, so that could be viewed also from this point of view. If I have a lattice like z to the n in Rn, at the scale of the lattice itself, it looks like dust, right? And that's right. You can't, right? You can only distinguish between finite groups. If you're in a compact group versus being in a non-compact group, that's all you can tell, by looking just at the topology of the lattice as a discrete set. On the other hand, if you begin looking at it as a metric space, all of a sudden you get more going on. Right? I mean, so it starts off being dust, but then after you go beyond a scale, right? So think about, say, z squared, right? So then firstly you begin filling in, the whole checkerboard. Okay? Then when you get above square root of 2, you then fill in the squares. And then after that, nothing else happens. So all of a sudden there's a 2-dimensional locally finite homology class that has infinite size. Okay, so all of a sudden there's a bar, and if you think about it, the z squared is included in the Lie group R2, and by looking at the bars that are larger than something or other associated to the lattice, you're able to discover the R2 that it sits in. So if I want to distinguish z squared from z cubed, this would be easy. Now, that's easy to do anyway because you could ask how many lattice points there are in a ball of radius r. But if I asked you to distinguish the hyperbolic plane from hyperbolic 3 space, they both grow exponentially, and I wouldn't be able to do this. But all of a sudden, this kind of thing tells you, oh, there is a topological information. So what this tells you is that when you translate it, by the time you're done, what this tells you is that the cohomological dimension of the lattice is this, at least that amount of the Lie group you could reconstruct. Some very primitive information, but I think that was really probably within pure mathematics the first time that this construction was used. But I could be wrong. But it's also very close to the applied thing. I mean, in the applied application, right, you're having sample points and you're trying to discover the object that it was coming from. And here, the sample points are the points of a discrete subgroup of the Lie group, and you're trying to infer the Lie group. Okay, so they're actually very close in spirit. Okay, so I just want to be applying the same thing to this, and I'm going to use log of the Lipschitz constant instead of the Lipschitz constant itself. Okay. So let me now do a slightly easier one. A slightly harder one. Okay. Suppose I look at maps from X to the circle. Okay. And I want to understand, okay, this is sort of another case which you could try to do. And this one also isn't so bad. So, suppose that I have F and G and they're homotopic. So, by the way, people should know, this thing here is isomorphic to the first cohomology group of the space, which is the same thing as homomorphisms of the fundamental group to Z, if X is connected. Okay? And, the interpretation, by the way, is just if I have a loop in X, and then I map that loop to the circle, then it has a winding number. And so I get a collection of integers, right? So this whole thing is always some Z to the N. Okay? And if you have Lipschitz constant L, then you're going to be within a ball of size around L, in that Z to the N. Okay, so we know that, so this is, right? So, so to speak, the number of homotopy classes of Lipschitz constant less than or equal to L is around L to the dimension of the first cohomology of X. Okay? And, this is, right, this is just sort of, straightforward thinking about this. Okay? And now, but, that doesn't, right, but now we have a language to say that we haven't discovered everything that we're interested in knowing, right? This is telling us, okay, that there are going to be infinitely many bars, right? And they're all going to have some birth time. And the ones with birth time less than L, right? The birth time is around some kind of norm on the first cohomology. Okay, you could build some norm on it. And, it's just saying that you're looking at the lattice points in the ball in this cohomology group. Okay, is there any more information here? And the answer is no. Okay, and the reason is, if I looked at the zero cohomology class, right, that would be the maps that are null homotopic. So by covering space theory, those maps, I could take the logarithm of them and get maps to the real line. Okay, and now the Lipschitz constant doesn't change. Okay, so, so let me say, I go from F is exp of log F, all right, where exp is the map from R to the circle. Okay, this map here preserves Lipschitz constants. Okay, so over here I could take, exp of T log F plus 1 minus T log G. Okay, and the path, and it preserves the exact Lipschitz constant. Okay, so that's what you do if you're null homotopic. If you're not null homotopic, you lift X to a suitable cover, and the maps, if they're homotopic, they're equivariant with respect to the same group action. It's sort of a nice exercise in a first course in algebraic topology to do it for all the homotopy classes. So what's happening is the persistent homology, when you give the circle the usual metric on the circle, what's happening is the persistent homology is very, very rigid. Something is born, and that really means that a convex set is beginning to exist. And then for all times after, it just, so the persistent homology looks like this. There's nothing above dimension 0. And in dimension 0, this is born at time 0. There are going to be, a couple of things that are born at time 1, some more things born at time 2, okay? And it's all infinite length intervals. Okay? And so, it's a little disappointing, right? This is nothing to write home about. There's a little bit more geometry here than just in, that you were measuring before, right? Which is when the birth time is, right? So when you have just infinite length intervals, the birth time is something that's of interest, right? When does something exist? And, there's plenty of geometry that goes on into such problems, okay? But, all right, so but this is the picture of what goes on here. And it turns out that what I described is the picture that always occurs when this target here is non-positively curved. Okay? And it's by some version of this argument. Okay? you have to, what you translate this is you pass to some cover, and then this thing here, you just think of it as being the unique geodesic in that cover that connects one lift to the other lift. Okay, so this kind of convexity is non-positive curvature. So now let's do the opposite basic case. Which is maps from S1 into a space X. Okay? And now here, the things of size less than or equal to L, right? This is, sort of these are the elements of the fundamental group of X that have length at most L. I mean, that's more or less the translation of it. Okay, so, and we know, and that this is, O of X of L, right? And, as we proved last time, or if you know about growth of groups, you know this fact. Okay, right? So that's the amount of stuff. But is there anything else that's going on? And so let's think about this. So let me try to draw, so this space here, by the way, is sometimes called the loop space of X. I should put in a base point, okay? To be honest, but I don't feel the need, okay? So I'm going to just draw the function space. So here I have X itself. This is the constant loops. And then, there's something or other here. And then, at some point or other, like if I'm on the torus, I have, there's this lattice point, the shortest distance, something else is born. Right, there are lots of these things. All the different components correspond to the fundamental group. Okay, but now what does it mean for two things to be homotopic? Right, so that's going to be, one curve is a guy here, another thing is a guy here. Right, to be homotopic, that means that there's some path, a family of curves that connects one to the other. Okay, and, there might be some homotopy that gets very, very large, right? So so let me look at, say, the component of the identity, right? The constant. I put an E here. It's of the trivial map, okay, which corresponds to these X's, to these maps here, okay? So PH0 reduced, okay, of, I'm going to call it loop E of X, right? So these are the loops on X that are, in fact, homotopic to a constant, which means, by the way, it has that persistent homology feel, right? I look at something here and I don't immediately know whether it's living in this component or not. When it dies, then I know when it was born, I know what was born, right? Et cetera, et cetera. Same kind of feeling to it. Right? So, at the point where I have a curve, I don't happen to know whether it's null homotopic. So I don't know whether it's, I don't know in which function space it is. I know it's in loops of X, but I don't know if it's in loop E of X. Okay, so that's sort of a funny thing about this space, which I'll exploit in a moment. So I could look at this, okay, with respect to log of the Lipschitz constant. Okay, and what is this telling me? And I could ask, what are the bars in here? So there's obviously one infinite length bar, right? Because the constant maps, right? That's what's born. And by definition, all the other bars are finite length, right? Something else will be born. But if it's really living in this component, it means that there's some place or other that you could, those components do merge at some higher level. Okay? So the bars of this, what? I took reduced because I'm not really interested in the trivial curves. Okay, right? So not only are they homotopic to a constant, they are a constant, and it's hard. Yeah, I don't want to study constants, because I can't. Spaces you could push around. Constants, they're sort of, you have to be strong to study constants. Okay. right? So the bars of this measure how long, well, let me say it like this, how hard it is to tell that a null homotopic curve is null homotopic. Okay, so what do I mean by that? So the fundamental group, for people who know what it is, people very quickly learn how to compute it from some decent picture of the space X. And from an explicit version of X, you can write down an explicit description of the fundamental group, and that's called Van Kampen theorem. Okay, so computing fundamental groups is in some sense algorithmic. Okay, namely, you get a description of the fundamental group that you can play around with. And now every loop in the space can be described in terms of these generators. Okay, and now there's a problem which is called the word problem, which is if I give myself a word in these generators, I now ask, is it trivial or not? And I'd like to have an algorithm for it. So if this group, it might be presentation very complicated. If it happens to be the trivial group, then the word problem has a trivial solution. Just always answer, yes, the word is trivial. Okay? If this were, say, I imagine generating the integers using the numbers 2 and the number 3, I would go ahead and I would take the word and I'd ignore the fact that in theory it's non-commutative, and I would just plug in 2 for G1 and I'd plug in 3 for G2, and I'd see whether when I reduce all this thing I get 0 or not. And that would be an algorithmic solution. Okay? Now the amazing thing is, discovered by Boone and by Novikov, who is the father of the Fields medal Novikov, discovered that there are finitely presented groups for which that algorithmic question is undecidable. Okay? So let's just think about what's going on in this persistent homology when I would have such a group. Okay, so then if I have such a group, then I would be taking a word, and from Van Kampen theorem, I know, each G1 corresponds to some loop, and G2 corresponds to some loop. So if I have a word, I know which loop it corresponds to. So I'm finding a point in this space. Okay, and now suppose that the persistent homology of this, suppose that the bars only had length at most 50. Okay, then what could I do? If I cut this off at level 50, all the stuff I told you about entropy yesterday says that this is a space that I could understand, right? I mean, I could put I could put in a very dense set of points into a computer, and I could put down a simplicial complex. And then what am I asking? If I start from here and I go up to, say 50 larger than it, which by the way corresponds to multiplying the length by e to the 50. Okay. I go ahead, I do that, and then, then I, build this nice simplicial complex because I know what are all the vertices of the simplicial complex, and I know when they're close enough to connect them. And then I could just ask, is there a path from this down to the constant? And if there is, if there is, then I know the curve is null homotopic, and if there isn't, and you weren't lying to me, about that every curve of length L that's null homotopic can be homotoped through curves of length at most e to the 50 times L, then this would be a completely good algorithm. Okay, so what does this say? This says that this thing here, reversing it, right? If there is no algorithm, okay, then then they're going to be arbitrarily long bars. Okay, right? I mean, it can't be that all the bars are size less than 50, less than 100, or anything like that, right? Because if there were some number like 1,000, then there'd be an algorithm associated to 1,000, and that would contradict the way I picked this group. Okay, so now, so that's so persistent homology is measuring the logical complexity in this case of the fundamental group. Okay, you can show that the bars can be bounded by a computable function if and only if it's algorithmically solvable. If you really want an if and only if statement. Okay, and you could also get more precise things if you're don't like unsolvable. You have some other measurements. There are things where it's not logically impossible, but it's just extremely difficult, and extremely difficult would mean that you have to go very, very high. Okay, so this is a way of translating into, say a more applied. This is so far, verbal, but it tells you, for example, that this question only depends on the fundamental group. It didn't really depend on the space X, which is sort of a remarkable thing. So I'm asking you, if I'm on a Riemannian manifold and I want to know, is every curve of length L that's null homotopic, is it null homotopic through curves at length at most C times L? That answer turns out, not only is it independent of the metric, it's independent of which compact manifold had that fundamental group, because all of those things have to do with just, are all the bars of this of some uniform length? Of course, for different manifolds, the constant C will be different, okay? Okay? And all of that is just sort of like built into this framework. And another thing that it tells me is, so if I think about Morse theory, having all of these bars of infinite length, at the bottom of every bar, there's a critical point. And what is a critical point of length? That's what we call a closed geodesic. So we learn that whenever you have an unsolvable word problem, then there have to be infinitely many closed null homotopic geodesics. Okay? And now these geodesics are very, very beautiful. They're not like the null homotopic geodesic that the equator of a two-sphere is, where even though it's a geodesic, but you push it slightly up into the northern hemisphere and then it's a little shorter. These are local minima. Not only are they local minima, they're sort of, they beat all competitors that are, quite high up. Anyway, you want to decrease the value of the length, you have to go up way, way, way higher. Not only down to the trivial element, if I just even wanted to go smaller, I have to go way higher by exactly the same argument. Okay, so by the way, that was a theorem of Gromov, that any manifold whose fundamental group has unsolvable word problem, there are always infinitely many closed null homotopic geodesics. And now we have even a way, we can add on a little more refinement. They're always what are called index 0. And we have a very, very crude and simple understanding of these. Okay, so, I have 10 minutes left. Okay, so I'm going to state a theorem and begin exploring it. Okay? So here's a theorem.
Well, maybe we should switch.
Yeah. I feel like, maybe after they have a night's sleep, they'll be ready to work again tomorrow. I'd hate to think that I killed these.
You don't have to say sure.
Yeah. Okay, so here's a theorem of Steve Ferry and myself. And it says, I'm going to tell you a more recent version, which is due to Jonathan Block and myself. But as just because this version fits into the terminology that I introduced better. So the theorem says this. It says, if X is a space with space, of course, again, means compact manifold with boundary. Okay, I'm not going to, with finite homotopy groups. Okay, ooh, this is really offensive. So if you want to have an example to keep in mind, just to be offended, take the projective plane and you take its suspension. Okay? It turns out that whenever a decent space has finite homotopy groups, you can certify it. Okay? I mean, you first somehow certify that the fundamental group is finite by finding a compact universal cover. Okay? Whatever. I mean, there's what to do, and then you calculate the homology groups of that cover. Anyway, but there are examples. Okay? Then, for any z, which is, say, a simplicial complex with standard simplicity, just if you want to think about, how to metrize it, just think about, you just glue the simplices together, completely standard. I don't want to, talk about weird things in. Then the persistent homology of the maps from Z into X. So let me just say, the finite bars of maps from Z to X, right, with respect to log of the Lipschitz function, okay, that these, the finite bars, all are of a uniformly bounded size, where the bound is some constant depending on I and the dimension of X. Okay? Okay? Okay, so and that furthermore, the ith homology, okay, so when the I goes up, the lengths might go up, okay, and also if I have a higher dimensional simplicial complex mapping in, that enters, okay, and furthermore,
So it's the dimension of 0?
dimension of Z, yeah. Yeah, because in my brain, actually, Z was the target and X was the domain. But anyway, you know, okay, furthermore, you know, if some pi I of X is infinite, this is false. Okay? All right? So, you know, at the moment I want to focus on the good news, but I mean, there's also a little piece of bad news. Okay? Which is maybe actually, you know, a good way for, you know, a middle episode in a series to end, right? I mean, right? I mean, no good news, and people, you know, it's just too depressing to keep watching, but if it ends on a high note, what's bringing you back? Okay, so firstly, this is saying that, you know, when you have finite homotopy groups, it's the exact opposite phenomenon that we, you know, that we saw in the logically complicated situation, right? Finite groups have solvable word problems because they have multiplication tables, and you could just use the multiplication table to see whether the group is trivial or not. Okay, so that works on the fundamental group, and then you hope that the rest works the same way. Okay, so you know, so somehow these kind of situations, finite homotopy groups, the theorem says that the simplest picture, the thing that we're used to from convexity and non-positive curvature, for some reason, seems to still hold when you have finite homotopy groups. Okay? And now, partially this is the phenomenon that came up at the end of last lecture as well, which is that things that finite homotopy groups are like simply connected, right? That you, just with a finite amount of nonsense, right, of passing to a cover, you're in the simply connected world. And the simply connected world, we said that sort of, we knew algorithmically that, you know, that there's a lot that's much simpler about simply connected homotopy theory than it is in general. And, you know, and that was due to the work of Serre. And in fact, this theorem is basically an application of the work of Serre in a more geometric way. Okay, I don't think I have time to explain much about it. So what this says is that, if, you know, in particular, if I apply it to pH0, it says that I have two maps, you know, F and G from X to Z, from Z to X, right? And they are homotopic. Then the homotopy that exists, I can actually bound what the Lipschitz constant is. Okay? There's always just some multiplicative constant that works. Okay? And so the second part of the theorem says that when some homotopy group is infinite, this is never the case. Okay? So, you know what? Yeah.
Does it spoil the result for all the other homotopy groups? Just one of them is infinite.
Yeah, no. When one of them is infinite, then below that dimension, things still work out okay. Okay, but then in that dimension and above, then life is bad. But what I realize is that this is not exactly the thing that I wrote. I mean, I realize that, I have to say something a little bit more refined. So let me correct the misstatement. Okay? So, indeed, okay, so now I want to add this indeed in here. So then once I've done that, then this becomes true, okay? Because what I said, you'll see in a moment, was wrong. Indeed, so if f and g map x to z are L Lipschitz, other way around, okay, are L Lipschitz and homotopic, there exists a C that just depends on the dimension of Z. Okay, I should say it. First, there is some constant just depending on the dimension, such that if I have F and G that are L Lipschitz and homotopic, then there exists a C L Lipschitz homotopy, okay, capital F mapping Z cross 0, 1 to X. Okay? So what's the difference? So a homotopy is a one-parameter family of maps. Okay, and this one-parameter family of maps, I'm insisting that at every time in that slice, that the maps are CL Lipschitz. Okay? And that's what's really measured by pH 0, of this function space. Can I find a path? But no one is, that path was just asked to be continuous. In this stronger statement, okay, and that's actually what the earlier theorem with Ferri produces, not only are you knowing that the individual guys are CL Lipschitz, in the time direction, you're also CL Lipschitz. So that, so think about it, right? I mean, if I have a space, I'm just saying that 2 points are in the same component, that there exists a path. I could always parameterize my path to be of unit length, even if they're 1,000,000 kilometers apart, right? But once I put in a Lipschitz constant, then I'm measuring something about the distance of those paths. Okay, so actually this refinement is what the point of next talk is, where I talk about diameter. Okay, so what this is saying is that not only are these things sort of almost connected, they're also sort of almost finite diameter, right? That, in the time direction, you're also only going a constant amount. Okay, so these function spaces, right? I mean, so the basic point is that somehow finite homotopy groups, they're looking as if the target is a point from just the point of view of the measurements we're doing. There might be several infinite length bars, but then each of those bars, in addition, there's just some finite amount of noise, and that sort of each piece is having some bounded diameter, at some level. So it's sort of like what people call small worlds. Anyway, I'll explain more of this next time. Yeah. So anyway, that's where the coming attraction is. For applications, you almost, for most of the applications, unfortunately, you don't have this condition. Okay, so it's a nice theorem that, that says that the contrasting situation does indeed contrast with the, with the geometric group theory kind of examples, or the logic examples, right? So you do see that strong contrast, so that's sort of nice. But the theorem that you get out of it, has relatively weak geometric applications, because it's very, very rare that all the homotopy groups of something are finite. What typically that means is that the problems that you're trying to solve, they only have finite order obstructions to solving them. Okay, so not only do I have to explain this, I have to explain, sort of what are there's some natural boundary here, and I have to explain, there's one more idea to go beyond that natural boundary. So, okay, so next time I'll draw some pictures. Okay, I'm going to focus on diameter, and I'm going to just draw some pictures. Okay, and then at some point I'll end, and thank you. So, well, thank you now.
lost with the last part because you gave the example of a non-positively curved space.
Yeah.
I one would be infinite, but there you do have this.
Okay, so good. Thank you. Okay, so. Yeah, okay, but let me just point out, so that's a great question, okay? And so it's obvious that the answer, I just have to deal with the case of the circle. So that's good news, because that's a case that I actually did, okay? So let's think about the map from R. When we think about two maps from R to the circle, one of these maps is the exponential, and the other one is the constant. Okay? These are two maps from R to the circle. Now you're going to see, okay? And these maps are in fact homotopic, right? Because I could, just take x of t times R, right? And, at time 1 it's this map, and at time 0 it's this. Wait a
When
second.
you say this is false, you mean you can choose z as well. I mean, it's not.
Yes, I'm going to choose. You see, right. So here it's a very strong thing. Not only is there a constant, the constant depends on the dimension, dimension of homology, but for our purposes, I equals 0 is interesting enough, right? Because that's this question about deforming functions to one another. Okay, so I equals 0, we'll just be content with that. But that the constant only depends on the dimension of what you map in. Okay, now that's sort of a strong condition. So what I claim, so firstly, so now here's going to be the logic. Okay, suppose that this was true with some constant, right, for maps of any one-dimensional thing into the circle. So maps, arbitrary things from the interval. So I could restrict the function here to minus nn, and this to minus nn, right? And I could then find a C L Lipschitz, L is equal to 1, so I could find a C Lipschitz homotopy, right, connecting one to the other, right, just on these intervals, right? Because remember, the constant is only supposed to see the dimension of the domain, right, not the structure of it. Okay, now, then I could use Arzela-Ascoli and tell me that a subsequence of these homotopies will converge to a C Lipschitz homotopy on the map from R, on these two maps from, right, either this map from R to the circle and this map from R to the circle. Okay, so that's the proof of the Arzela-Ascoli theorem enables you to take a subsequence of these things. Okay, all of the homotopies with a given L is a compact space. I have the space at scale n. I have the space at scale n plus 1. There's a map from one to the other, and now I'm taking an inverse limit of compact spaces. So by the Tikhonov theorem, if they're all non-empty, then there's some point in that inverse limit. Okay. So Voila, that's Voila is French, by the way, there would be a C Lipschitz homotopy between these, okay? But now, can there be? No, I mean, if you think about, that's just sort of, this thing here, I would lift all of this to the real line. Right? I mean, because after all, these are all contractible, so I would lift to the real line. And now on here, the distances are getting linearly apart on the lift, and over here, the lift is a constant. So, when I get to distance n, the constant c has to be at least n, okay, or 2n or something like that, right? So, so it's just very clear that you can't, that. There's something, and what it tells you is not that that if you cared about a specific z and a specific x, that you're not going to have the persistent homology. One is because persistent homology still isn't the right tool to capture, this notion, the CL Lipschitz homotopy, which turns out to be the thing that's more useful for geometry than the actual persistent homology. Okay, right? I mean, that's the thing that tells you the distance between, the path that you choose. But it also tells you that so when the target has finite homotopy groups, you don't have to pay any attention to the geometry of the domain. the way to turn this around is that if you still hope to get theorems where you allow your z's to have infinite homotopy groups, you have to apply them in situations where you control the geometry of the domain. Okay? Now that already begins raising new kinds of questions because, for example, in topology, lots of times when you reduce problems to algebraic topology, they're in stable homotopy theory, so you get to play around with the domain a little bit. Which dimensional sphere do you map in and things like that. I mean, it's sort of, so there's a tension, there's a resolution to the tension, but then that resolution raises new problems. Okay, I mean, it's life, it's math. Okay. So, that's sort of where we're heading. Okay, but anyway, great question, because it's exactly what we have to struggle with. Okay.
Any other questions? Okay.
All right.
So we're resuming tomorrow at